So, thanks everybody. Sorry about that. My name is Matt Hardy. I'm the Program Director for Planning and Policy here at AASHTO, where I'm the liaison for a number of committees in charge of performance management, asset management, and then planning. This webinar, Know the Risk, GeoTechnical Assets as Key to Improving Performance, is the second of two webinars on geotechnical assets and transportation asset management. And these are being sponsored by both the FHWA Office of Asset Management, thanks to Steve Gay, and then also AASHTO's Subcommittee on Asset Management, which is chaired by Anant Prasad. Vice Chair is Tim Henkel, and they're from Florida DOT and Minnesota DOT, respectively. Back in May, but May 2013, we had part one, where we had four different presentations on geotechnical asset management. And then today, and you can view a recording of this. We did record this webinar. The recording is available if you go to tam.transportation.org. It is available, and you can look at it and view it and see all those four great presentations. So today, this is part two. We have a lot more presentations, I think, to go through today. So here on this slide, you can sort of see Scott Richrath from Colorado DOT is going to provide some introductory remarks, and then Ty Ortiz, also from CDOT, is going to talk about their rockfall management system. Matt DeMarco from the FHWA Central Lands has a couple presentations. Don Turner from Oregon DOT, and then Jim Higbee from Utah DOT, and we'll round it out with Ken Fishman from McMahon and Mann. So these are the about 6 or 7 presentations that we're going to go over today. As these folks give their presentations, you can use the Q&A feature up at the top. If you go to the little handlebar kind of thing, there's a Q&A. The best way to ask questions is to type them in there. And at the very end of the presentation, we will do a sort of an open Q&A, and I will sort of moderate that for everybody. But if you can type your question in there, we'll be sure to get to it. The learning objectives for this two-part webinar series: 1, develop an understanding of the role of geotechnical assets in the performance of transportation systems. Learn how to consider risk and implement asset plans designed to improve performance. And then listen to case study presenters share their experiences with programs for rock, soil slopes, and retaining walls, and learn what others have accomplished. And then finally, learn what state DOTs and federal agencies are doing to manage their geotechnical assets. One of the focuses of the Subcommittee on Asset Management here at AASHTO, and I think FHWA as well, is to sort of get beyond just what we consider asset management as pavements and bridges, but there are many other assets that we have to consider as well. Safety, your ITS, your technology, signs, pavement markings, all those great things. And geotechnical is another one of those sort of asset classes that we have to consider. At this point, I want to turn it over to Steve Gay from the FHWA Office of Asset Management, and he wants to say a couple things, and then he'll turn it over to Scott Richrath. So, Steve, go ahead.
Thanks a lot, Matt. Yeah, I think Matt just said, Map 21 talks about state DOTs having to develop an asset management plan that talks about pavements and bridges. I know some states are thinking about addressing other assets, and Scott will talk about that in a couple of minutes here. Just want to point out that there's another webinar coming up on this Wednesday at the same time in dealing with the Asset Management Book Club, and then there'll be a webinar on July 10th on asset management and performance-based planning. Matt referenced documents or videos available from webinars up on one of the websites. Also, please visit the FHWA Asset Management website. Just last Thursday, we posted the work plan for developing an asset management plan from New York DOT, and I'm hoping that we have the work plan for developing an asset management plan from Minnesota in the next week or so. So at this point, let me turn it over to Scott Richrath from Colorado DOT. Scott? you, Steve. This is Scott Richrath.
And I'm the Transportation Performance Branch Manager. And Steve or anyone, Matt Hardy, can you hear me?
Yes.
Okay, great. And I'll introduce the first speaker, Ty Ortiz, with whom I work here at the Colorado DOT, but he'll give you the technical presentation on the rockfall management plan here at CDOT. And I'm going to give a little bit broader perspective, not only in Colorado, but perhaps what we're doing to work with MAP 21 federal authorization. As many of you know, MAP 21 requires development of a risk-based asset management plan, and we kicked off the development of that plan just a couple of months ago here in Colorado with the intent of completing our first iteration by December 31. We know that that will be ahead of rulemaking, and that rulemaking will prompt additional changes, but we don't want this plan to be just a plan that we develop and put on a shelf. We want it to be dynamic. We want it to maintain an ongoing list of ways we can improve the implementation and the actual decisions that are being made with that plan. So we're actually excited about the fact that we're going to have a plan developed in front of rules, and that rules will give us an opportunity to revisit that plan, enhance it, and make it more useful moving forward. One of the things within that plan that's really important that I think a lot of state DOTs are struggling to define and determine how they're going to build that in is the risk-based portion of that plan. In Colorado, we're taking a programmatic look at risk, but also a systematic look at risk. And we know that we don't want to go completely enterprise-wide with all risks that face CDOT, but we know that many of the risks that face CDOT on a daily basis are risks that can impact our assets. So those of you that saw presentations on the first part of this webinar back in May will recall Scott Anderson from Federal Highway talking about the corridor concept and how you can bring to light the underserved geotechnical assets by demonstrating the impact that those assets or failure of those assets can have on the corridor. And you may also recall a presentation by Mark Vesley of Shannon and Wilson, who presented on risk-based methods for management of geotechnical features and transportation infrastructure. Well, we decided here in Colorado that as part of our risk-based plan, we wanted to leverage the work that those folks had been doing, and we wanted to bring the geotechnical assets into the risk-based asset management plan, which, as Steve points out, is mandated to be applied to highways and bridges, but encouraged for use of all assets within the right-of-way. And sometimes when you talk about geotechnical assets, you're even talking about assets that might lie outside of a state DOT's right-of-way. Well, the work that Shannon and Wilson and Ty Ortiz, whom we'll present here in a moment, are doing revolves heavily around risk. So we thought we'd try to take some of the work they had done on identifying risk and apply that to a lot of different risks facing the department. So we looked at risk defined as probability times consequence, and we realized fairly quickly that the probability of an asset failure, the probability of a landslide, the probability or the risk portion, the probability portion of risk is often best determined by the asset managers themselves. We rely on Ty to tell us, how many rock falls have you experienced over this stretch of the highway over the past X number of years, and we do somewhat of a probability calculation there. We go to our staff bridge engineer and rely on him to tell us what's the probability of a bridge failure. But when we get to the consequence portion of the risk calculation, we now want to make that more broad than just a rockfall management plan would indicate, or than just a bridge engineer would calculate. We want to look at the consequence of interrupting service to the corridor, the consequence from a safety standpoint, from a mobility standpoint, from a public relations standpoint. So when we build that formula and when we try to quantify risks as we build our risk-based asset management plan, we're going to rely on not just asset managers, but on a number of other folks to help us determine what that consequence is so that we can better prioritize how to put investment to the different assets. So we're building, if you will, a decision tree of sorts that will look at project level, corridor level, and program level decisions, funding decisions, policy and procedure decisions that we have to make. Right. And risk will become a part of that decision tree at various different points. And we have to look at risk not only in the average risk, but what are the outliers? What are those catastrophic occurrences that might have very low probability but very high consequence? Or what are those things that occur far more frequently than we think they're occurring, and we've never really quantified or monetized the consequence portion, if you will, because we thought the consequence was so small, but we've underestimated the probability. So as a result, we could have a dedicated funding program that looks to address risk department-wide before we even move into the life cycle preservation dollars that drive about half of our annual budget. Or we could look within each asset to make sure that we're appropriately applying risk, with risk being different for bridges than it is for surface treatment. So that's how we're addressing the risk-based asset management plan in Colorado today. Ty Ortiz from Colorado DOT will next talk more specifically about the geotechnical assets that we have that will live within that plan, and he'll talk about our rockfall management plan. So thanks everyone for joining the webinar, and I will hand it over to Ty, I believe.
Thank you, Scott. Can you guys hear me okay?
I can hear you, Ty.
Thanks. So right around 1996 or so is when CDOT kind of formally initiated a rockfall program. And as with most states with rockfall hazards, we use a rockfall hazard rating system. And over those, almost 20 years now, we've used a top-down approach to allocate resources to mitigating rockfall sites. And so over the years, we've kind of stepped back and try to take a look at how efficient that has been. And so if we go to the next slide, we'll see a map that shows all of our rockfall sites statewide, and there's over 750 of these things that we evaluate, that we look at. And we have, over that since 1996, mitigated only about 70 of these through our rockfall program funding. There have been other sites mitigated, perhaps as corridor or other projects that have come along for highway improvements, but specifically to rockfall, it's only been about 70 sites. And our goal here, though, was to reduce rockfall on a statewide basis, right? So obviously we've mitigated or reduced rockfall risk at that one particular site, but on a statewide basis, it didn't seem like we were very effective. And so I think the next slide kind of gives a good example of that. This is what we would refer to as the Clear Creek Canyon Corridor. It's a corridor from Denver to one of our nearby mountain towns, Black Hawk and Central City. And there are about 50-plus sites to this location. So a good percentage of our rockfall sites are within this area. Well, if you go to the next slide. Oh, back one. So since 1996, we've only mitigated 12 of these sites. The green dots indicate sites that have been mitigated. So just visually, you can see that over that 18 years or so, just a small portion of sites, even in this really heavily traveled corridor, have been mitigated. And so it seemed clear that we wanted to try to do another approach because we've all seen the issues that can happen when we have rockfall events. And so what we decided to do was put together a rockfall management plan rather than just a simple rockfall mitigation plan that was site by site. And so if we go to the next slide, when we put together this management plan, we put together kind of a makeshift mission, so to speak. And this was to help us stay on track, stay on goal with what we wanted to do with our plan. And our goals were really to reduce risk on a statewide basis. And because rockfall is considered an asset, right? It's a hazard, but that hazard really affects the hazard of the highway, or the hazards associated, the assets associated with the highway to help us to get from point A to point B. But to do that, we needed to be able to measure what we were doing. We needed to be able to measure the performance of rockfall. And we hadn't really thought about that before. We'd gone and mitigated, but we really hadn't measured anything, partially because we didn't feel that we had data, and we had never done it before. We didn't really know how to go about measuring performance. And so go to the next slide. What we ended up with is a rockfall management plan that really addresses three things that we do within the Colorado Rockfall program. And the primary function for us right now is to reduce risk. And once again, I'm going to keep on going back to reducing risk statewide, because that's our goal, is to reduce the rockfall risk on a statewide basis. The other things that we do is as we get more and more mitigation performed, we have more and more devices that we need to manage. We need to replace fences. We need to replace barrier along the highway. We need to replace netting. And in some cases, we need to update that netting. Then the third thing that we do, and everybody that has states with mountain areas are used to this, right? We respond to emergencies. With a good management plan, we think we could probably reduce the amount of emergencies that we respond to, but it's not realistic to think that we would ever get rid of all of our emergencies. So if we go to the next slide. So to reduce the risk, and that's what we're really going to concentrate on, we wanted to take a corridor approach. We felt that if we could mitigate an entire corridor of rockfall, that would kind of provide us a larger statewide risk reduction for rockfall. But with the same understanding that not all of our sites that have a high risk are going to fit into a corridor approach. So we wanted a method that would allow us to consider sites that were outside of corridors also. And if you guys, for those of you on the seminar, if you've not seen this photo before, there was nobody hurt here. This car was not occupied at the time that this rock fell on top of it. This particular road is pretty heavily traveled.
Yeah, I can. All right, okay. All right, I will get it.
And, sorry, I got a little distraction here. Yeah, but anyway, this person wasn't in this particular car when it happened, but he was parked there. It's a very widely used rockfall climbing area, and this was a parking location for the rockfall climbers. And so traffic, parking, all of that seemed to sort of tell us that, maybe this corridor that has a lot of traffic, has a lot of people parked there for recreational use, should be something that we give a high priority to. So if we go to the next slide, the first thing we needed to do was divide our state into corridors. And what we have found is that within CDOT, we didn't have really a set method to delineate corridors. And so we needed someplace to start. So what we did is we just sat down with this map and we divided the state up into our rockfall sites and just used geography really. And geography combined with just our empirical experience of the mobility to get from different locations within the state. And going back to the traffic scenario, I wanted to show a couple of examples of sort of how traffic comes into play for us when we start to prioritize these corridors. And I'll get to sort of what all these dots mean. These dots represent different sites, so I'll get to what the different colors mean here in just a minute. But if we go to the next slide, we can see a couple of examples of traffic corridors. So this is a corridor that only has about 1,400 AADT. So it's a relatively small volume compared to other locations around the state. But this type of event that you see here happens, on average, and just based on my experience, probably happens every 2 to 3 years we will get an event this size. Clearly, it's a road closing event. If we go to the next slide. So this is a corridor, this is that same Clear Creek Canyon corridor, it has about 10 times the amount of traffic. And so even little incidents like this will close the road just because there's so much traffic. It's clear that whenever there's rock on the road, somebody's going to hit that, and there's a bigger chance for a rock to actually land on a vehicle. And so it just seems very clear to us that traffic seems to be a big part of trying to prioritize our corridors. And so the next slide will show the method that we use to prioritize them. And we had kind of a two-tier or two-step phase. You had to make it through step one to even be considered as part of our priority. And that first one was traffic volume. And so we are kind of using traffic as a surrogate of the consequence of rockfall. And it seemed to make sense, right? Where we have more traffic, there's obviously a bigger consequence to the highway, but there's also a bigger consequence to the surrounding community in terms of getting people and goods and things like that to the different towns. The second tier in prioritizing a corridor was the likelihood of a car being affected by rockfall. And we're using the term vehicle exposure here. And vehicle exposure is determined by taking data points from a rockfall hazard rating system and combining those. We use AVR, average vehicle risk, which for all intents and purposes is the percentage of time throughout the day that a car is within the rockfall zone or the rockfall hazard for that particular site. Site distance plays a big part of risk, right? If you can see it happening, you can probably stop the time. And we use accidents as well because our accident data may not be perfect. We use it as a component of state patrol, but it's an indicator at least of what's happening. The last thing here is the reduction factor. So this reduction factor is incorporated into this as the means of kind of adding a probability to this. And an example of a mitigation reduction factor would be ditch. If the site has a really good ditch, we have things like Ritchie ditch charts or the Oregon rockfall catchment area design guidelines that kind of give us a percentage of rock captured scenario that can be applied to this. So if we have a ditch that is catching 95% of our rocks, well then we can reduce this. We can multiply this by 0.05 for a likelihood, because the goal, even if rock falls from the slope, the goal is really to keep off the highway. And so the next slide kind of emphasizes vehicle exposure. What we think we're going to try to do, or what we decided to do, is use this vehicle exposure component to measure the performance of rockfall, and to measure the performance of our rockfall mitigation. So if we go to the next slide. So now that we had a method of prioritizing our rockfall corridors, that's exactly what we did. The dots that you see here, we have traffic. We use high, medium, and low traffic volumes, and we use high, medium, and low vehicle exposure numbers. And so the sites that were delineated with red dots are those sites that have both a high traffic count and a high vehicle exposure. And so for us, given the amount of money that we have, given the time that's going to take us to work on a corridor, we right now are going with just the red dots for delineating or prioritizing our corridors. And so if we go to the next slide, what that tells us, though, is that once we have our corridors delineated, and it doesn't really show it very well in this particular slide, but once we have them delineated, we would really kind of stop looking at sites as individuals, and we would look at corridors as a whole. And you can see right here our Tier 1 corridors, at least. The rest of our state, the corridors of the rest of our state are shown here, at least on my screen, though they're not showing up. They're colored blue. You can kind of see the outline of those corridors. The thinking now is going to be that instead of looking at individual sites, we're going to need to look at an entire corridor. And there's going to be other hazards within that corridor also. There are going to be landslide areas. There are going to be debris flow areas. There are going to be rock slide areas, obviously rockfall areas. And so you might think of this as a geologic hazard zone. And these red Tier 1 corridors are going to be where we start. Well, that still leaves us with our high-risk priorities. So if we go to the next slide. Our high-risk priorities are still going to be important to us, because we understand that not everything fits into a Tier 1 corridor that probably has a high risk or that we should be paying attention to. And so we're going to take a cost-benefit ratio to look at prioritizing these high-risk sites. And so along with mitigating sites through a corridor, we're also going to mitigate sites that have a high risk that don't fit within that corridor. And the benefit for these are going to be measured by the amount of vehicle exposure reduction that mitigating one of these high-risk sites presents to the corridor. Next slide, please. So Once we have our sites delineated and we have the existing corridor, the vehicle exposures determined, at least an average vehicle exposure, our next steps now are going to be to enter into feasibility studies for these corridors. One of the concepts that we're going to have is to kind of take a mitigation confidence factor. And what that's going to tell us, or what that's going to be, is the effectiveness. I'm trying to put a number to the effectiveness of the type of mitigation. And this might be be done on a broad basis, like the type of geology, or it could be done on a site-to-site basis, giving the type of mitigation scenario that you might see. So if we go to the next slide, we might start evaluating our mitigation scenarios based on kind of a trade-off, cost-benefit or investment-to-benefit scenario. So we may have A, B, and C, D scenarios for specific sites. We may have A, B, C, and D scenarios for specific corridors, but the goal is going to be to do this mitigation, perform this mitigation to a corridor performance target. And right now we're at a place where we don't have these corridor performance targets because we didn't feel we had enough information to provide them. So we're going to enter into these feasibility studies for our Tier 1 corridors, and at that point then we will see what is an achievable performance target for us. And so with the next slide, that would be the end of what I have to show for what we're doing in Colorado for rockfall.
All right, can you hear me?
Yep.
Okay, this is Matt DeMarco. I head up the GeoTechnical section of Central Federal Lands Highway Division of FHWA out of Denver. And I'm going to talk about an engineered slope management program that we kicked off at Yosemite National Park back in the summer of 2011. Dovetails very well with what Ty was just talking about and has some elements of his statewide program in a much smaller area. So I think it will align well with what you just heard. Prior to 2011, the park had experienced a number of severe rockfall events that had closed roads and hampered mobility and were serious safety concerns. And it was just about the same time that the TRB, Geotechnical Asset Management Subcommittee, was kicking off its new mission to bring awareness to geotechnical assets. And so we saw this as an excellent opportunity to not only engage in a park-wide inventory and assessment program for engineered slopes, but to also start this dialogue and including them as assets to be managed like any other asset in the park. So on this slide that you have, there's about 130 miles of roadway that were included in the survey. You can see the roads there in red. All of the main park roads, from a rockfall risk standpoint, all have very similar safety issues, similar types of rockfall aspects of the roadway, two-lane roads, 35, 40-mile-an-hour speed limits, congested at different times of the year, mobility issues throughout the park. All of the main park roadways are have entrance stations in and out of the park for mobility for not only visitation but also for the 1,000-plus workers that support vending and other services within the park, as well as all the emergency exit, egress and ingress in and out of the park. Constructed assets, retaining walls, decorative guard walls, other types of features like that are similar. I did throw one item on here on preservation that might be a little bit different than in a state program. The view shed for the traveling public is an extremely important resource within a park. And so where Ty had that list of a number of different mitigation options that could be deployed, those types of things are very difficult to get started or implement within a national park just because of the aesthetic value and aesthetic issues that surround them. So some similar types of things from a state program, but otherwise pretty standard risk elements throughout this smaller microcosm of the state program. Our approach was to locate, assess, and rate slopes using the rockfall hazard rating system. Also to relate cut slope hazards to park global studies. I'll talk a little bit about that in a minute. Again, recommend a palette of mitigation strategies, and this was a strategies of escalating rockfall mitigation measures that might be tolerated within the park. And then finally, and probably most importantly, was to frame identified roadway hazards related to engineered cuts within the road inventory program. Each of the parks within the Park Service has a road inventory or pavement preservation type program that serves as the main asset, principal asset for the park. All other assets, whether they're bridges, culverts, signs, traffic barriers, buildings, all hang off of that main road asset. And so we wanted to tie all of our engineered cut slopes to that same program to emphasize that we're going to be treating these as assets. Next slide. Rockfall has been an issue in the park for decades and has been studied by U.S. Geological Surveys well over the last 30 years. And April of last year, the park geologist Greg Stock, along with USGS and others, published a risk assessment for major rockfall that had been occurring in Yosemite Valley. This is an excellent publication, and you can access this very easily by simply Googling Yosemite rockfall, and it'll come up with this document. And the upper right photo there that shows the plan view aerial, you'll see a thin red line. That was a hazard line or a risk line that was established for the park based on this analysis that is now being used to drive policy on decommissioning some camping areas and actually removing some of the residence headquarters within the park. Next slide. I should have mentioned, too, that I think it was because of that more global study that's been ongoing within the valley that the park really understood the value of rockfall management and understood where we wanted to go with the engineered slope management program, and so it was an easy sell. As I mentioned, we use the rockfall hazard rating system as our basis for our work. It's a hazard assessment. It has some risk attributes to it, not a true risk measurement program by any stretch, but easy to apply. It does provide a basis for funding prioritization, though could be misused in a worst first kind of context, and we'll talk a little bit about that. And our deployment was pretty traditional with a preliminary screening of over 300 slopes on the park roads. We wound up conducting a rating assessment of 163 of those cuts. And then we followed up with some months later with a windshield survey that involved all of the maintenance staff traveling all the roadways. When you're out on the ground collecting this information, you get this snapshot in time of performance, but you don't get a sense of how the cuts are performing seasonally. And so we just did a very simple 1 through 5, kind of hold up a finger as we drove by as to how serious or a rockfall issue each of these sites were. Lined up very well with the RHRS survey. Next slide, please. This just gives you a quick picture of the types of slope issues that we're dealing with within the park. They can range anywhere from decomposed granite in the upper left that really just produces a lot of small material out onto the roadway, but is not a big rock producer, to exfoliating granite, bowling alley type situation in the upper right, daylighting joint structures with sliding blocks, wedge blocks predominant over a lot of the park on the lower left, and then the most hazardous situation predominantly on Tioga Road, where we have a lot of glacial deposited grounded boulders that are eroding from very soft soils coming from on high. Extremely hazardous situation. Next slide. So over the course of the work, we did this 163 cuts were rated, looked at how the ratings were falling out, and just very simply did a quick distribution of the types of remediation actions that needed to be done to each of these slopes, and to have a very simple conversation with park engineering and maintenance staff, we broke them into 150 rating elements, point elements, and then classified them low, medium, high, and very high. Again, this aligned very well with the windshield survey. Next slide. You can see the distribution of how those ranked out. The very low were excluded in the original screening, so the 163 ranked from very high to low. 85% of the slopes ranked medium or lower, and we only had 15% that ranked in the high category. And this would have been where I think traditionally, from a programming standpoint, we would have said, okay, let's go out and start doing the engineering on our highest, what appears to be our highest risk, 2%, maybe breaking into that 13% in the high category, and get our out-year funding in place so we can go to work and fix 3 or 4 slopes at a time. Very similar to what Ty showed on the Clear Creek example with having attacked a handful of the higher risk slopes, a few at a time. The conversation that we wanted to have with the park at this time and pursued was, let's take a look at, and could you go to the next slide, please, is rather than jump to the conclusion of attacking high-risk slopes, what is it that we really want to pursue over the next 5, 10, 20 years? And is it possible for us to set some sort of target performance rating for within the park? And when we looked at the maintenance requirements and the mitigation measures, there's kind of a natural break around that 300 RHRS rating. We said, well, is this a good target for us? Can we reach that, giving due consideration to a number of factors? And let's look at the next slide, please. And some of those considerations have to do with immediate funding. You know, what monies do we have in pocket right now that we can apply to imminent hazards within the park? Where are we going with program funding in the park? We have highway work, roadway work scheduled for the next 9 years in the park. How can we leverage those funds towards a broader program? Is there a cost-benefit consideration that we need to give to treating a larger volume of slopes as opposed to focusing in on some of the larger, higher-risk slopes? And then a couple of issues that the park has to address on resource impacts and policy directives. The park, of course, with the Yosemite Valley issues, has come up with substantial policy regarding rockfall, and so we have to align our work within those policies. And then the bottom one here on park delivery. With sequestration, a number of people have been laid off from the park, and so there was a big push that perhaps the park could deliver some of this work. And so we can go on to the next slide, please. So we came up with a 3-phase program aimed at addressing those types of considerations. In the first phase, that actually kicked off just this morning in the park, we called hangar removal. And it has to go back to, and again, I think Ty just talked a little bit about going back and looking at the highest risk locations in the state. The question came up in the park that if we wanted to allocate several $100,000 to try to drive medium-rated slopes into the low-rated, where we're treating maybe 80 slopes as opposed to 2 or 3 slopes, are we ignoring imminent hazards and dangers within the park? And what doesn't come out in the rating system is these sites that have imminent hazards. And so in this particular case, which is on Wawona Road, which is the first road they're starting on this morning, you can see that this slope doesn't really have much of a rockfall hazard related to it outside of this one boulder that's perched up at the top of the hill and is just hung by a tree root. So we took a step back and said, you know, for a couple $100,000 and putting park staff to work, you know, we can go to a lot of the slopes immediately this year and not have to wait for program funds out here and make a positive impact on safety throughout the park immediately with the skill set that they have. Next slide, please. And as it turns out, that park staff actually have a lot more skill than we gave them credit for, and probably mostly due to the fact that they're all trails and hiking trail and climbing foremen that have worked in the park for a lot of years. They're going to put their hand scaling efforts to work and start tackling some of those 80 medium rated slopes on mostly scaling and ditch recovery. So for the next 2 to 5 years, with funds that are available now through this year, through fiscal year 14, as well as leverage funds from some of our paving program, the park will be delivering the lion's share of immediate scaling work and driving those 80-some slopes from a medium rated down into a low rated, reducing safety issues and reducing maintenance costs moving forward. And then finally, for the very high-risk slopes, the engineering programming will start later this year, looking at major rehabilitation, reconstruction, realignment of roadways. The photo that you see here, the large photo, has plenty of room to move this road out onto the shoulder, and this is programmed for 4 years from now. Get us away from having to do any type of rock treatment up here. Next slide. So in closing, I'll just say that pretty rudimentary. A first start at changing a paradigm within the park on managing rock hazards and proactive approach, and also beginning to the first steps of incorporating this subject into their asset management program park-wide. And I'll just say also that Mark Besley spoke in May about geotechnical asset management. I think he made reference to the new document that came out of Central FHWA on implementation concepts and strategies. And I just would say that this is now available. It's new this year, and some of these same subjects are covered in there as well. And you can Google geotechnical asset management, and this will come right up. Thank you.
This is Matt Hardy. I'm gonna redo the lecture mode one more time. Give me 1 second.
All callers are muted. All callers are unmuted. All callers are muted and may unmute themselves by pressing *6.
So next up, I think Matt, you're up again. So if you can hit *6 to unmute your phone.
Okay, this is Matt. Can you hear me?
Yep.
All right, we'll just jump into the next subject. I'm only going to talk about the first couple of slides here. I think our state folks have asked for a little more time to present. This program, the National Park Service Retaining Wall Inventory and Asset Program, was initiated back in 2004, ran through 2009, has been reported on in a number of different venues. All totaled, if you're not familiar with it, we ran an inventory and assessment on 3,500 retaining walls across 33 of our nation's largest parks. And like I say, it reported on the results on that in a number of different venues. Next slide. And if you simply Google NPS wall inventory, the full manual, procedures manual, 200 pages of how we did it, and all of the processes and procedures for data collection, the acceptance criteria defining what a wall is for the NPS program may be very different for a state program or for a municipality, but we'll show you what we did there. Field forms, field guides, the data management, all of those types of things are covered in detail in this manual. And perhaps the most important thing is the data definitions library. When you set about inventorying and assessing structures that have a lot of different flavors to them, we had over 23 wall types that were included in our small, relatively small wall inventory for the Park Service. There can be a lot of details, and the devil's in the details of this program. So I'll just throw that out, that I encourage people to pull this up and take a look at it. It's been used in a lot of different venues. Most recently, it was translated into French and used in Haiti for the Haitian disaster. So there's a lot of good legwork's been done here already if you haven't begun to pursue this subject. I think Matt, I think at this point we'll pass and go on to the state presentations.
Okay. So I think next up is Don Turner. So Don, if you can hit *6 to unmute your phone.
Can you hear me?
I can. Bring up
Okay,
the
great.
presentation now. There you go.
Okay, very good. Thank you. Yeah, I'm Don Turner. I'm with the Oregon Department of Transportation, geotechnical designer. And I'm going to be talking a little bit about our retaining wall management system and just a brief overview of it. Thank you. We started our program in 2007. We developed, in stages, we developed a geotechnical design manual, which we never had before that. And with that, we incorporated some wall definitions that we could then put into our asset management categories. We instituted a structure numbers process. Previously, only bridges received structure numbers, and now walls also receive them. We have a retaining wall management system database that we've collected, and we developed a beginnings of an inspection criteria for that and incorporated into the database. And then we have, as part of the inspection criteria, we developed a first level condition assessment. So basically looking at the wall, seeing if it's performing as it needs to, and then develop further criteria after that. Next slide, please. Some of the definitions, we have defined bridge retaining walls, anything that supports a bridge end or is close to the bridge, as opposed to, in this case, a highway retaining wall, which is separated from a bridge and is standalone. It can be MSV, they can be tieback walls, anything that else that is standing alone. Next slide, please. Part of our process that we developed was to collect information in the office from existing as-constructed plans, going through each plan set and trying to determine what the intent of the design was at the time. This could go back 50, 60 years, so sometimes it's quite difficult. Anytime we see a wall in those plan sets, we incorporate it into our database as a database record. We used all that information coming from the plans to get a type, size, and location of the wall. And then we follow that up with a field verification of each wall and try to do a first level condition of that wall. That's an ongoing process we're into right now. Next slide, please. The database itself was developed using the National Bridge Inventory coding field and Pontus data, so that we could tie all of the information directly into our bridge section. Because so many walls are part of the bridge prism, we wanted to make sure that we weren't recreating something separate from our bridge section. We also used the Colorado DOT feasibility paper by Hearn, which used Pontus type information, and then the FHWA circular on earth retaining structures. Next slide, please. This is just a screenshot of our first page of our database. It's probably too small to read, but it just shows that there's a lot of information that you can gain out of a set of plans just to get a type, size, and location. Just basic information, and gives you an idea then of where to get started. Next slide, please. The condition rating is probably the more difficult thing to do at this point. There's no standard yet on condition ratings for walls, other than what our bridge inspection folks use to inspect bridges and abutments and those kind of things. So what we developed is a simplified version, what we call a total element score. We use what we call primary elements, which is the primary element of a wall is the face. It's the only thing you can really see of a retaining wall, so that's the primary element. Secondary elements are anything that surrounds the wall. And then we have performance elements. The rating score uses a bunch of multipliers to try and help out how good the data is, and we're planning on improving all this as time goes on. Next slide, please. So just an example of primary elements is the wall face. In this case, it's an MSE wall, as opposed to secondary elements, which can also affect the wall. So if you have guardrail, if you have slopes above or below a wall, if you have coping, any other appurtenances to a wall, any paved road, any structure that might be nearby, buildings, anything like that. Next slide, please. So what have we found so far? We have about 2,100 bridge and highway walls in ODOT. About 60% of the walls we have now constructed are MSE. By that I mean, I don't want to confuse it. By that I mean walls that are now being built. Years past it was more cantilever. Now most walls are MSE type. About 10% of walls now being built are cantilever. About 70% of all the walls that are built are part of a bridge. And 90% of walls that we have are under 30 feet high. Next slide. So what have we learned so far? Our design information can be very scattered. We have to go to bridge files. We have to go to our archive as constructed plans. Sometimes project manager files contain information that aren't in the plans. Another option that came up, another thing that came up in later years, we started giving contractors the option of several different types of walls to build. So the plans probably didn't show what was actually built. So that means we have to go out in the field and look and see if we can determine what that wall might have been. As constructed plans, older plans are different from newer plans in that how much information was incorporated. And then as all part of this, sometimes construction resulted in a wall being added during construction that might not have shown up in the plans. And then part of the complexity of MSE walls is that there's many pieces. There's reinforcement, there's wall-facing elements. So you might have to have shop drawings to go along with all this. And another part of this is what is your communication with maintenance? Certain walls get repaired out in the field by maintenance that we don't know anything about here in the office. So having a good communication process with maintenance is important. What's the next step? We're going to be developing inspection responsibilities with our bridge section to work with our bridge inspectors. We have to develop wall rehab procedures for different types of walls. MSE wall would require something different than a tieback wall. Communication and reporting process for new wall construction, and some sort of process for electronic submittal of shop drawings. After that, we need to have some sort of a life cycle cost analysis method developed. Next slide, please. So at present, our wall program competes with other assets, signs, guardrail, ADA ramps, slopes, culverts, for funding. At this point, culvert inventory is getting most of the funding, and so our walls program is moving slowly forward in just trying to develop one piece at a time. And if we can get more funding, we'll work on it in a faster method. And that's all I have. Thank you.
All right. Thanks, Don. Next up, we have Jim Higbee. So, Jim, be sure to hit *6 to unmute your phone.
Can you hear me now?
I can hear you.
All right. Thanks, Matt.
All right, Jim.
I'm going to talk about our UDOT retaining wall inventory inspection asset management program, which is still in its infancy for us. In talking with Dave Stanley over the last few years, and with Don here last Friday, I've come to realize that we at UDOT have really had a leg up in terms of our starting point for developing an effective asset management program for our state's retaining walls. This is from two main aspects. The first being about 15 years ago, our Structures Division adopted a wall numbering system, but like other states that started similar numbering systems years ago, our folks began to assign numbers somewhat haphazardly for things that had nothing to do with retaining walls. After a few years, they refined the process to assign them only to walls, and more recently, they've adopted an efficient email system for project designers to formally request the wall numbers, while giving us more definitive background info on the walls. The numbering is currently up to about 740, but we certainly have a lot more walls in the state than that. The main reason being is that we've generally followed the numbering process that only one wall number is assigned for all the walls of a particular type on a project, or for a project phase where that applies for our larger projects. So, for instance, on the Legacy Parkway project located north of the Salt Lake Valley, which was completed in 2008, there were only 3 wall numbers for all 40-some-odd single-stage MSE walls for each of the 3 project segments, and 2 numbers for the 2-stage walls on the 2 wall segments. And so to identify the individual walls for each group having the same base wall number, we use letters behind them. So on one of my recent projects, we got to wall W, meaning we had 22 walls on that particular wall number. So that's our nomenclature briefly. The second and most important aspect of the starting point of our wall asset management program was a state-funded research project. We have a rather comprehensive and active research program at UDOT called UTRAC, and don't worry about what that stands for because we don't remember ourselves, but it centers around an annual workshop conducted by our research division, and it's well supported by federal highways and our 3 largest local universities and by members of our local transportation industry. And if we do say so ourselves, we in the UDOT GeoTech division have a rather strong seat at the table with our UTRAC program. And that's in large thanks to a strong precedent set by one of our former top-notch research engineers with a strong geotech background, Blaine Leonard, who went on to become the national president of ASCE a few years ago. And also with a continued strong support by a current research engineer who's also a geotech, David Stevens. Next slide. So in our 2006 UTRAC workshop, we, the geotech section, helped promote and advance a research project. Next slide. With this title, and I wish we would have got the word inventory in there someplace, but the project merged into one from 2 initial proposals by Utah State University, Go Aggies, and BYU, with Dr. Jim Bay from USU and Dr. Travis Gerber from BYU. Next slide. This was quite an ambitious project. Their goals, next slide, were to locate and collect all the available drawings, specs, wall designer calcs, and so forth, as Don mentioned, that related to our MSE walls throughout the state, to develop an inspection procedure for the MSE walls, to conduct all the inspections of some 3,000 or 4,000 some odd walls that we could find, to develop a GIS-based database for the walls, which contains wall locations, drawings, specs, and inspection info, and to compile a synthesis of the wall conditions, to perform a statistical assessment of the wall inspection data, and lastly, to convene an expert panel to evaluate perceived failure modes of our MSE walls, and to make recommendations regarding the design, construction, and maintenance of them. So beginning under watchful care of Blaine Leonard and our research division, and continuing with David Stevens, they conducted this project over a nearly 3-year span. They got bogged down at a couple of points. They did a pretty good job in wrapping it up in the fall of 2009. Due to some logistical issues, we haven't been able to get a final report yet, so I can't forward that around to anybody yet. But we hope to be able to share it at some point with our GAM committee and other interested people. So then the inspection phase, the inspection data gives us a baseline against which future wall performance can be assessed. In analyzing the data, the number of MSE walls with potential performance issues were identified. So this list of problem walls that we have, we hope will provide us with a potential means of prioritizing future inspection efforts when resources are limited, as they are for most everyone. Next slide. As a background for the research team, we provide them with information we have gathered concerning a few of our problem walls. And here's just a couple of quick examples. In the town of Clearfield, Utah, we had a MSC wall abutment, and we had abutment walls around multiple railroad tracks that experienced several modes of failure, including undermining and displacement of the wall leveling pads, vertical separation between the wall panels, rotation of the panels with accompanying spalling of several panel corners, outward rotation of the top wall panels and coping, and cracking of the coping, and so forth. And then about 4 years ago, after completion of the $1.6 billion I-15 reconstruction project through Salt Lake, we saw some buckling of MSC wall panels for these 6 north ridge abutment walls, which were two-stage walls designed by the now assimilated BSL Wall Company. They used a welded wire mesh reinforcement grid with the facing panels attached to the mesh by turnbuckles. When we inspected the back of the panels, we saw that corrosion had deteriorated one of the connections between the panel and the turnbuckle. So we theorized that the corrosion of the connection allowed the panel to lose rotational restraint and buckle. And we repaired the worst spot right here with a CIP concrete section. Next. So the 2 research inspection teams from USU and BYU did their statewide wall inspections in the summer of 2007. Next. They developed a very comprehensive inspection form and procedures with sections on the wall inspector and general wall info, summary of key observations, plan and drainage views, cross-sections, and specific wall characteristics. I don't know if you can read a lot of that, particularly on the right side. It's pretty dark here. But I'll briefly show you a few of the situations that they uncovered in their inspections. This is one of my oversight projects in beautiful Logan Canyon. We have eroded backfill and exposed geogrid reinforcement due to the poor surface drainage design. They come across that one. Next one. We like our walls to be self-drained, but this is ridiculous. There was a storm drain connection issue for the abutment wall west of I-15 in Salt Lake here, where the designers unwisely put the drainage right through the MSC reinforced zone, which we know is something we very much want to avoid. Next one. Sometimes the contractors and our inspectors mistake topsoil for MSC backfill, and this is the kind of flora that is created going out of the wall joints when they do that. Poor excuse is a joke. We try to firmly adhere to the federal highway requirement to provide a 4-foot wide bench in front of MSC walls that have slopes below them. And here are a couple examples of an adequate bench and an inadequate bench. And they're both on the same project there, as you can see. Looks like we were cut off on the bottom side here on our slide, at least. Sorry about that. And the next one is my favorite wall inspection result from the research team. This MSC block wall is located in a rural part of southeast Utah that has very little opportunity for anyone in the public or even for UDOT forces to see it very often. This erosion seriously undercut the leveling pads, leaving this section of the wall suspended with no support. If they hadn't seen this problem and alerted us so that we could alert our maintenance forces, we could have had a serious safety problem on our hands for the overlying state highway. So for our database, I won't talk much about all the details that you can read here for yourself, but suffice it to say we had a GIS-based database, and it used the MS Access program for its platform, and it seemed to work pretty well for them. Next slide when you want to. Having a database system to retain your drawings and specs, inspection reports, and photographs and so forth, that becomes critical when you're assessing a potential future of occurrence of a poor wall performance or a failure. Your previous inspections can also provide a baseline of MSC wall conditions against which you can assess your future conditions. But without baseline information, for example, it might be hard to assess whether cracking in a wall occurred during construction and is no longer a concern, or whether cracking is the result of an active mechanism, which is continuing to degrade the wall's integrity. But with proper documentation of the wall's behavior and its design and construction, it's possible to stop, delay, or rectify potential problems before they reach a critical point. So for our expert panel, here's the particulars of our panel that you can read. They evaluated multiple issues regarding the design, construction, and maintenance of our walls, and they distinguish between short-term and long-term maintenance concerns. Short-term being considered 15 years old or younger, and long-term being 25 to 75 years old. The short-term concerns focused on wall drainage, wall design, details and specs, and the retention of our wall information,
but the long-term concerns focus mainly on the degradation of MSE wall systems, primarily the metallic reinforcement, as Ken Fishman's going to talk about here. So where have we gone, and where are we going from here? With this strong starting point, we didn't want to let potentially very good wall asset management program drop away from us. So in December of 2010, 2.5 years ago, we prepared an action plan with proposed funding options for our structures management to take before our Utah Transportation Commission. Things didn't go as well as we'd hoped for at that point, so we've been in a holding pattern since then. But recently, in preparation for this presentation, I contacted one of our managers and asked for his general feelings on helping us move the program forward. He replied to me back last week with a general but good statement of support. So we're optimistic, I think, that we can get our program going in the not-too-distant future. Thanks.
All right, great. Thanks, Jim. Then last up, we have Ken Fishman. Bring yours up. So Ken, it's up. Don't forget to hit *6 if you need to unmute yourself.
Okay, can you hear me?
I can.
Okay, I'm going to talk a little bit about collecting performance data from one particular type of geotechnical engineering component or structure, which are MSE walls that are reinforced with metallic reinforcements. And as Jim mentioned, this does represent a rather large segment of the retaining wall inventory, particularly for retaining walls that have been built recently and for projects that are currently under construction. I want to talk a little bit about how condition assessment and performance modeling, which is really going to be some of the detailed discussion that I'm going to go through in this presentation, how this kind of relates to the overall asset management system. Certainly, we have to receive from another level within the organization directives in terms of what the goals and policies are relative to asset management. I mean, they're either trying to improve safety, improve efficiency, lower cost, but we have to be sure that the data that we're collecting and the way that we are interpreting it is actually going to feed into the system such that we can check and see how these goals are being achieved, if they are indeed being achieved. And then finally, once we collect the information, it has to be passed, back up the line, so to speak, to those people that are going to be making decisions, etc., based on this data. Next slide, please. These systems do prevail throughout highway systems in a number of different applications. Next slide, please. That do include bridge abutments, bridge approaches, highway embankments, depressed highways, etc. And as you can see from these photographs, these can be rather substantial structures, and the performance, durability, etc., serviceability of these elements do indeed affect the performance of the entire system. Next slide, please. In terms of performance, it helps to look and see how these walls different components are, but essentially an MSE wall, we usually have a relatively light, often precast concrete panel, set of panels that are articulated and form the face of the wall. These panels have connections to reinforcements that are actually embedded in fill as the wall is placed. And the soil that makes up the wall fill, as well as the reinforcements, are also very important components of the system. And some of the problems or some of the issues that might come up might be issues related, to the wall face itself, might be related to some erosion or drainage problems, as Don and Jim were discussing, as well as the performance of the reinforcements themselves. And what I'm going to focus on, because others have talked about some of these other issues, is really the performance of one particular element, which would be the reinforcements. Next slide, please. There are a number of different types of reinforcements that are in service right now, and these have developed over the years since these walls were originally introduced in the later 1960s and early 70s. But we have individual steel strip type reinforcements that are often connected to precast concrete wall facing units. We might also have, as you're seeing in the lower left-hand photo, mats that are often welded wire mesh that are wider elements and are constructed from cold-run wires that are welded together. The strips are often hot-rolled steel products. And in the lower left, these mats are also attached to precast concrete wall-faced panels. But it's also possible to have a wire-faced wall, which is what we're seeing in the lower right photo, where rather than having precast panels constructed as part of the system, the wall facing is actually a wire face as well. So you have a wire mat for reinforcement and then a wire face that's bent up and actually reinforced with a backing mat often towards the face. So in fact, the whole structure is actually a metal wall. Next slide, please. The reinforcement performance is affected very strongly by the character of the wall fill. And often the wall fill, or not often, the wall fill is specified and has to meet certain requirements in terms of gradation. And these are intended to give you the strength as well as the permeability that you need for the fill material. And often, particularly with metallic reinforcements, the wall fill has to meet certain electrochemical requirements to try to mitigate the potential for corrosion and other issues that might affect the durability of the metal reinforcement. So we try to limit the pH, the resistivity, as well as the salt content of the wall fill. And as long as you meet those criteria, what we've seen is the performance of metal reinforcements within different fill types is really been quite good. In fact, usually it's better than what we assume in design. So one of the lessons, or one of the points that I want to make with this presentation is when we're looking and studying performance, it doesn't help to only look at bad performance. We can certainly find examples of bad performance. They abound in the literature. Usually, or always, this has been attributed to some poor quality backfill that has been used, and in fact should not have been used to construct the wall. But there's also a vast amount of data that shows relatively good performance. So I think this is some good news that can be used by asset managers, and I think that when you're collecting data and trying to analyze it, you have to be careful not to only look at the bad cases. You have to look at performance as a whole and try to distinguish between good and bad behavior and group them accordingly. Next slide, please. There are two main documents that I'm really going to speak from. The first document that you're seeing is this FHWA document, Corrosion Degradation of Soil Reinforcements for Mechanically Stabilized Earth Walls and Slopes. Has been around for a while. The first version of this came out in 1990. It was written by a guy named Victor Elias. And that first came out with a procedure or a process, a number of techniques that can be used for condition assessments of these reinforcements. So a lot of the techniques that we're using for measurements are really coming out of this document. And at this point in time, these measurement techniques that we're using are really considered to be mature technologies. So we're no longer looking at trying to improve the measurement technique itself, but more looking at how to process and interpret the data that we're getting from these measurements. The second document is much more general, and it just recently came out. I think it came out towards the end of 2012, and this is an NCHRP synthesis that was actually written by one of the researchers that Jim Higbee just mentioned, Travis Gerber from Utah. And I think basically this synthesis is a takeoff on what he did in Utah, describing their asset management program for retaining walls. And what it does is kind of describes very well all of the activities that Utah, as well as other states, have undertaken to develop inventories and develop some performance indices, etc., for retaining walls. And what was done with the federal lands program is also included in there. I'm not going to talk much about it. It does get in a little bit to some of the corrosion monitoring and the durability issues that I'm going to discuss, but it's a little bit more general to that, and I really encourage you to take a look at that if you have an interest in retaining walls and following up what Don and Jim and Matt DeMarco had talked about earlier. I think it's really a well-done synthesis. Next slide, please. In terms of performance monitoring, certainly there are a number of objectives that we want to achieve with this, not the least of which is just to try to verify the validity of the corrosion rates used in design. Are we going to be doing better or worse than what we thought? How does this affect the service life? And how will this affect decisions that must be made as to extending the life of the highway system on into the future? But there are certainly a lot of other aspects of performance monitoring that can be used to address problems as far as identifying where your best fill sources are, what's the effect from extreme events, flooding, etc., on the performance of these walls. Can we get some warning if we have an impending failure, and several other things. But I think in terms of asset management, right now we're kind of most interested in looking at the corrosion rates that we use in design and how do these kind of compare to what we're seeing. Next slide, please. There are two real general categories of ways to assess condition and measure corrosion rates. One is direct observations, which is the way it's been done since the early days when the suppliers were coming up with documentation and research to support the durability of their product and the corrosion rates that they were recommending to use in design. But essentially, these were often weight loss measurements or loss of thickness or strength measurements. We actually had to retrieve a sample, test it once, and get an answer, and then that sample is no good for further testing. You have to go back and retrieve another sample that may or may not be performing the same. But since the 90s, we have been implementing electrochemical tests, which are more of a non-destructive type of a test in order to measure corrosion rates directly. These techniques have the advantage that you can continue to monitor a single sample time and time again because you're not actually doing anything to disturb or cause any degradation or destruction of the sample itself. So it does have an advantage where you can continue to monitor over time. Of course, you have the disadvantage that you're often not getting a good look or a direct observation of what you're testing. So we recommend these days that there's still some direct observations done to confirm the electrochemical measurements and the results that you're getting from these non-destructive tests. Next slide, please. The testing requires that we install either some coupons or dummy elements during construction, or we attach wires to in-service reinforcements or somehow retrofit an installation for an existing wall. The pictures that I'm showing here are actually coming from California, where they got into the practice of installing what they call dummy inspection elements into the wall during construction. They're relatively inexpensive to place, and they come out through holes that are cast in the wall. They originally didn't put these in with electrochemical testing in mind, but since they do come through the wall face, we do have the ability to attach a wire to the end of the reinforcement and perform electrochemical testing, which is an advantage. Plus, these elements, as you can see on the right-hand side, can be extracted as well for direct physical observation. So some of the more recent studies that have been done in California have been to take walls where they may have as many as like 72 of these elements installed. They put them in clusters of 18, so they'll either have 2, 3, or 4 clusters, depending on how big the wall is. We can actually take electrochemical measurements on every single one of them and then decide on the basis of those measurements which ones you might want to extract and take a look at. So out of the whole batch of 70 or so, they may pull 2 or 3 for extraction. And without getting into details, I'll tell you that extraction is not that easy. It's somewhat of a challenge. It certainly takes a lot longer than the electrochemical test. It's very worthwhile when you get an element, but I think without the electrical chemical testing, it would be very difficult to get a lot of data from these elements. Next slide, please.
Hey, Ken, this is Matt. You have about 5 more minutes.
Okay. Yeah, the next slide, this just shows how you might install elements in an existing wall. Often we have to core through the wall face or chip through the panels to access reinforcements, and we can use these same holes to install short coupons or dummy elements. Next slide, please. This just shows one of the advantages of electrochemical testing. This is a site in New York. Behind one panel, there were 5 strip reinforcements. They put holes beside each of the 5 strips. And then we could do electrochemical testing. The plot on the right shows testing that was done really once a month throughout a 2-year period, and this kind of gives us some idea how corrosion rates might fluctuate with respect to time, how they might be affected by levels of precipitation, etc. And I think there's certainly a lot more work that can be done in this area. A lot of times when we put these in, we only read them once or twice, but I think on selected sites, you can get a lot of data if you can read these continuously. Next slide, please. We have collected a lot of data from several states that have implemented these wired reinforcements for electrochemical testing over time. This includes California, Florida, Georgia, New York, North Carolina, and several others. And this was all done as part of an NCHRP study that's now NCHRP Report 675, and I encourage you to have a look at this to see some of the details of the data. Next slide, please. But one of the things we did in this study was to group the data according to the character of the backfill. So we have some data that applies to what we're calling good quality backfill. This meets AASHTO criteria, but not by a wide margin, and other data that describes very high quality fill that does meet the AASHTO criteria by a wide margin. We see some differences in the performance. Certainly, the difference with high quality fill is superior to the performance that you get with good quality fill, and the good news is that more than half of the walls built in the United States are actually constructed with high-quality fill. So we might expect better performance than we anticipated in the design from most of the walls that have been constructed in the U.S. Next slide, please. So we need to take these data and do some type of reliability analysis with it so we can put this in a form that decision makers can use. Next slide, please. And there's a number of different ways to present these data. One of them is just to look at the expected service life, which is the plot that I have on the right here, and I'm just describing the probability of failure relative to the number of years that it's in service. In other words, if something has been in service for 100 years, what's the probability that the reinforcements have not lost too much cross-section? And this can be affected by fill type. So I've got some that are poorer quality fills and those that are the higher quality that I'm calling coarse aggregate fills. And also, certainly, the metal loss model that you use in design can have an effect on your expected service life. So those red lines there are where we're actually using more sacrificial steel in design. And so you could actually take a poorer quality fill and get a performance that's similar to what you would get in a high quality fill if you add more sacrificial steel. Next slide, please. We can also look at the probability that the tensile strength exceeds design requirements. So we're looking at more than just the metal loss. We're also now looking at the variation that might be inherent to tensile strength. And then finally, something that is done in load and resistance factor design, we can look at the probability that the load might exceed the resistance or vice versa, basically looking at what resistance factors we should use in design. Next slide, please. So I think there's a number of applications of the data that we can use for management. We can manage risks. We can do a lot of work with life cycle cost analysis. This feeds into management decisions and also what we should do towards the end of the wall life. And finally, next slide. I think there are a lot of utility of the data for asset management, particularly when it comes to life expectancy. We may be very interested to know that many of these walls may actually be serviceable well beyond 100 years. Certainly not all of them, but a large segment of the population may be in that category. And there are some other what I think are management objectives or decisions that can be made in terms of selecting backfill sources when you're in the construction stage and trying to have some more control on that, and really what we're going to do with older walls. And when you do have a distressed wall, is it the whole wall that's distressed, or can we define just a certain portion of the wall that might need to be rehabilitated? In other words, what's the extent of the problem? Thank you very much.
Thanks, Ken. Let me bring up the, it's about 3:30, so I think we started about 5 minutes or 7 minutes late. So we will use that time for some Q&A. So I'm going to bring back up the slide here with the presenters on there. And if you could use the Q&A feature at the sort of the handlebar, the toolbar for the live meeting service, that'd be great. So right now we have 2 questions. So the first one, I'll just sort of go down the list here. The first one is from Wyoming DOT. I'm not sure which presentation this was referred to, but in Colorado, for the AVR calculation, it uses crashes and site distance. Are crashes only ones identified as involving rock fall, or are other crashes included? Also, is the site distance a field estimated number at the rock fall location, or is it highway geometry driven? I guess that one's for Ty from Colorado. I can repeat that if needed. Are you still on the line, Ty?
Can you guys hear me?
Yeah.
Yep.
So the site distance was done by AASHTO Green Book determination, and it's done by the guys taking the rockfall hazard rating system build data. So they put the object out on the corner, and they kind of walk up. We don't walk down the middle of the road. We walk along the side of the road so you can see it, and they measure that distance. The crash, the accident data, it comes from our Colorado State Patrol, and they have two tags for accidents specific to rockfall. One is rock on road, and one is rock off road, and only those two tags from the Colorado State Patrol are taken into consideration for accidents.
All right, thanks, Ty. There's one question about finding the presentations and the recordings of the webinars from Part 1 and for Part 2. If you go to tam.transportation.org, and then I'll ensure that the Part 1s are there. I thought they were there. I'll make sure of that. But there's on the left-hand side, there's some bars, some navigation bars. You click on webinars, and it's under. It will be under there. I'll make sure. The next one, there's a question from George Davis for Matt DeMarco. George, all I have is for Matt DeMarco with no question. So if you can type out that question, I'd appreciate it. And the last one that we have so far is from Amir. Here we go from Matt. In the Yosemite rockfall study conducted by USGS, they used a model for a rockfall analysis called STONE. What do you know about it?
I'm sorry, I don't know anything about the STONE program. I'm not familiar with it any more than what's limited amount of information is provided in the USGS report.
Okay. All right, Amir, if you can finish typing in your question, I'd appreciate that one. And then Kevin McCain, has the Colorado DOT or Central Federal Lands used LIDAR to evaluate movement in slopes or walls?
Matt, do you want that, or do you want me to take it?
Go ahead, Ty. You can start.
Yeah, we've been experimenting with, all different types of remote sensing, LIDAR, NSAR, ground-based SAR, and photogrammetry. The LIDAR information, boy, we really seem to have faith in it. But like with anything else, the further we get away from it, from the source area, the less accurate we seem to be. We have one site in Glenwood Canyon. Our source area is about 900 meters from where we could set up the LIDAR. And it didn't particularly work at that location because we couldn't see any more accurate than about 5 inches of movement. Outside of that, the only other place we really used LIDAR was for a couple of landslides, and it was really for before and after type of, see what it's done over the last couple of weeks type of movement for design purposes.
Yeah, I'd add that we haven't used LIDAR or any other type of remote sensing for retaining walls. We have some limited experience with landslide measurement and in recent years, but by and large hasn't been part of our inventory type program.
All right.
We are using LIDAR for design, though. We've been using it quite a bit for quantities. Almost every project now has a LIDAR aspect for quantity determination.
Anybody else? Don, Jim, Ken? All right. So last question from Amir. The question is generally for everybody, but more specifically for Ken. Are you aware of any guideline or program in place for monitoring retaining wall movement as a performance measure?
I am not. In fact, one of the, if you're talking specifically about the durability of the reinforcements in terms of corrosion monitoring, etc., it was tried, and there's really no evidence that there's any outward sign of distress due to corrosion. You can even find, staining, rust staining on a concrete panel that may or may not be related to a problem with the soil reinforcements. Which is why we kind of got into this non-destructive testing technique, was because we realized we actually have to get some way to inspect and observe the condition of the reinforcements directly. In cases where walls, have actually suffered some type of a failure, like the one that picture that Jim was showing in Utah, these just happen all of a sudden. I mean, somebody just kind of drives by one day and sees it. It doesn't seem to be something that develops slowly over time. Certainly the metal loss does, but it's more of a brittle failure mechanism when it does occur.
Okay. Anybody else? Jim, Don, Matt, or Ty? All right. Well, it's 3:37 according to my clock. I think we've hit the mark. So I want to thank everybody for attending today. I especially want to thank the presenters, Scott, Ty Ortiz, Matt DeMarco, Don Turner, Jim Higbee, Ken Fishman. We all have busy jobs, and to take time out of the day to present at one of these webinars is greatly appreciated by all your colleagues out there at the different state DOTs and anywhere else that people came from to participate. Steve Gay, if you're on the line, I didn't know if you had any closing remarks, anything you wanted to say? You got to hit *6 to unmute yourself. Hearing nothing from Steve Gay, I'll say thank you. Or I guess anybody else who was the organizer? Scott Anderson. Anybody else? All right.
Yeah, Matt, thank you. This is Scott Anderson, FHWA. I'll just speak for the agency again here and thank those of you who did take the time out to make the presentation. Very good, and I think combined with the first webinar on some more general topics, it gives some good background and some a foundation, if you will, for some upcoming work in geotechnical asset management. So thank you very much for attending, and thanks to the speakers today.
And just a reminder, if you go to tam.transportation.org, we'll make sure the Part 1 and Part 2 recordings are up there, as well as the actual presentation. So, again, thanks a lot.
Yep. Thank you, everybody.
Right.